thing your computer? Oh, that's a circle.
Yeah.
Okay, look at all the notes on mine.
I guess it works. I just don't want it to fall.
Just make sure to return my wallet.
I'll take the gift card. Bless you.
So today I'm just going to do some examples that will likely be on the, not this coming exam, the exam Wednesday, by the way. There'll be a online portion. I'll give it a couple minutes. Hold on for wait for more people. But today we're just going to cover the final bit of chapter 10, I believe, or 11. And I believe it's 11. And some of these problems will show up on the next exam. Not this coming exam, but the next one. And we are near the end of this course where I could either just go in order. So the next chapter would be like elasticity and what do you call it? An equilibrium system, so static systems and such. We will go through this chapter, but depending on how long we spend on it, is really kind of up to the class. Because the chapters kind of get random at this point. Because we have elasticity and equilibrium systems, and then the next chapter, I believe, is gravitation. And then after that, it's oscillations and harmonic motion. And all three of those topics are very different. So I guess we'll see. But I was thinking we jump to harmonic motion first and do that chapter, because that chapter is just math. I know I say that all the time. It is a lot of math, but all that math is very useful for the other chapters. So I don't know. It depends on the complexity as well. So I guess we'll just go in order for now. But if we come across a topic that delves into another topic, I might just go over that topic right then and there. So. All right. So last time we had torque is equal to the tangent force times the radius. Right? So this came about from this. And by definition, this is RF sine theta, where theta is the angle between them. But if you just look at this piece here, this is just R times F. Okay? So we went over that, and it is important, we're going to go through and derive some more things. It's important to know that these two properties are very, very different. So, what? Sorry?
How was that times 10 kilowatt?
Oh, yeah. So I'm going to draw a picture here. Hold on. So you have R, and you have some force, but this thing's constrained, right? It has to only move like this, right? And if we were to draw this here, this becomes theta, right? And we just broke up these components. You have, let's say this was the path of motion. So it's a circle, right? So you have this tangent component, F tan, and then you have this, I guess you could call parallel component, F parallel. And it's parallel to the arm, so the radius, right? So you could write F as F tan plus F parallel, right? And if we were to do this, tau r cross F would just give us r cross F tan plus F parallel. And if we just factor this through, we get tau is equal to r cross F tan plus r cross F parallel. So if we just look at this here, this becomes r F tan sine theta plus r F parallel sine of sine phi. And I just picked phi because phi doesn't really show up here. Since F and R are pointed in the same direction, phi is just equal to 0, right? So they're pointing, see that F parallel and F, they're pointing in the same direction, so the angle between them is 0. So you're just left with R F tan sine theta, and then theta here, sorry, I drew this kind of wrong. This is theta between F, not theta between F tan. So let's make this a different angle. Let's make this alpha. So where is alpha on this image if we were to draw it? I'm going to ask you guys in the next exam to draw all of the locations of things, right? So I'll give you a blank diagram, and then you're going to have to draw where the variables are, okay? So where on this image is alpha? If I were to draw it, where should I draw it? Is it here, 1? Or is it here, 2? Or is it here, 3? Where does alpha go? Does it go at 1, 2, or 3? Someone says 3. Any other brave guesses? 2, okay. Any other guesses? It's actually 2, right? So the way you do this is you just move F tan to this location, right? And now what's the angle between F tan and R? Well, it's this one here, right? And so the angle between them is 90 degrees, and so this is just pi over 2, and sine of pi over 2 is just 1, right? So also this needs to have a little unit vector there. So this becomes tau r F tan n hat. And which direction is n hat pointing out of? Is it in the table or out the table?
Out the table.
So I put my hand in the direction of R, and I curl it in the direction of F. So my n is pointing out of the table. So n is out of the table. Okay. So that's what we covered last time. And a little summary of relationships here. We found that the sum of all torques is equal to I alpha, and you have to pick a direction of rotation. A lot of times people just choose Z. But this could be in general, really. This vector could be pointing in any direction, and you're just looking at the rotation about the axes. And Z could be any direction that you define it. Your book wants to point out relationships or similarities, so this is very similar to F external equals the mass times the acceleration. We're going to see a lot of these similarities. Okay, so what about the energy of the rotation? So if we were to look at a particle, let's say a wheel, there's a piece of it called your rotational velocity, right? But it's also moving, right? So it's moving this way, so you have a piece of it called your center of mass velocity. And to an observer, it's just the sum of these. Right? So this is just a piece of mass, it's called this mi. And if we were to do this, this would be ki is equal to 1/2 mi vi, so this is I. VCM is the same for all particles, right? And so, this is square, ki equals 1/2 mi VCM plus V root square. And this is for an I. Sometimes you'll see people just put an I down here. That means it's the I. It's for the I thing. So these two things will have an I next to it in general, in what they call Einstein notation. These subscripts we sum over, right? So there's a hidden sum here that we're not really writing down. I haven't wrote it down. In fact, a lot of the times when I write these indices like this, and I don't write down the sum, I am secretly teaching you Einstein notation, because I am not writing the sum. Normally in Einstein notation, you don't write the sum. You just write it as is, and then you expand it and you go from there. Okay, but this is not that course, so, you know. Okay, so we expand this out. 1/2 mi VCM squared plus v rotation I squared plus 2 VCM dotted VR. So I just expanded it out. And now we have, so I'm going to draw this angle here, I'm just going to call this angle theta. Notice that this theta is not the same as this. Let's call this alpha. Actually, no, alpha is used for acceleration. Let's call this beta. So notice theta is not the same as beta, right? So if I were to ask if I ask you to expand this out, and then I ask you which do you put in here? Do you put beta or theta, right? You should kind of know which one. I drew it kind of explicit here. So this becomes 1/2 mi VCM squared plus 1/2 mi v root I squared plus 2 VCM v root I mi times 1/2 cosine of theta. Okay, I'm going to add back in the sum. So this becomes the total mass, VCM squared plus 1/2, and I'm going to write this out a little differently. If you recall, this here is just Ri plus Ri omega I. Well, omega is the same for all particles, right? They're all rotating at the same location. So this would just be omega squared plus mi VCM v root I cosine. In fact, this would be an I as well, theta I. The reason why it's theta I is because you could look at a component here, right, and its angle is this way, and this would be a different theta, right? So all these thetas, i's have to be summed over. Okay, so we did the first sum, that's the total mass. The second sum, if you notice, we have mi/ri squared, right? And if you recall, that's just the inertia I, right? Omega squared plus, and then we have, I'm going to write this out a little differently. Dm, VCM, V rot cosine theta. Notice that this mass now is an integral, so we're going to integrate over this entire wheel. But by doing that, we have to integrate over all theta, right? And if you recall, any integral of d theta cosine theta from 0 to 2 pi is 0. So this term will give us 0. And then we're just left with the total energy as 1/2 times total VCM squared plus 1/2 I omega squared. And because this is with respect to the origin about a symmetric point, it is likely assumed that this is also the central mass. But it doesn't need to be. It doesn't need to be. Okay? Any questions on that? So let's do some examples. I like your book's yo-yo example.
Can I take a picture of that?
Oh yeah.
We're going through lower.
I highly recommend. So a lot of engineers, they know the minimum equation, right? But or the fundamental basic one. A lot of engineers will know this, but they forget how to derive it and the conditions for derivation, right? So if you know this, you can kind of derive it for any system that you want, right? So just keep that in mind. All right, let's do the yo-yo example. Your book does this example. I kind of like it. So you have a yo-yo, there's some tension, there's a weight, and it's not moving initially, and then you let it go, right? And then the yo-yo goes down, and then it eventually stops, and then spins at the bottom, right? And the question is, what's the relationship between the what is the relationship between the energy from its height, how much energy goes into its rotation, right? So
Professor, can you
our
move the paper
initial
down?
energy.
Can you move the paper down?
Oh, sorry. So there's a initial energy where we have K translational plus K rotation plus U grav. So our translational kinetic energy initially, we can just say 0, right, because it's not moving. Its rotational kinetic energy, we're just going to say it's not rotating initially. And it's at some distance, let's call this H. So this is just equal to mgh, right? And then our final kinetic energy, again, our translational, it's not moving, right? So that's 0. It's rotational, it's spinning, so let's do 1/2 I omega squared. And then let's put this as a 2 here. And what else? Okay, and its gravitational potential energy is spent, so let's just say that's 0 as well. Okay, and just based off this, right? K, E, K, F, we have mgh is equal to 1/2 I omega squared. And so the speed would be 2 mgh over I, square root is omega. So if the object, so a little fun question. let's say this yo-yo squeezes and contracts as the string unspools. So as it reduces down and sinks to the lowest point, the yo-yo shrinks. It becomes a smaller ball. The question is, will the frequency increase or decrease? Does anyone want to guess?
Increase?
Well, increase, right. And why is that?
Smaller mass, the same.
Same mass, it's just shrinking.
Not smaller.
It's because this I here, right? So I is equal to the sum M-I-R-I. R-I, right? R-I. This is R-I here. R-I. It's pointing to some object, right? So if my R-I gets smaller, right? So if R gets smaller, so less than, I don't know, just say goes small, then I goes small. So the more something shrinks in size, the smaller its inertia gets, assuming the mass doesn't change. So the mass is the same, but the object itself is shrinking, it's making itself smaller, right? So, I don't know if you guys ever seen this little experiment. What we'll do is, I think I wrote the example. Oh yeah, I did. Okay, we'll do this. Alright. Okay, so let's just do it for a disk here. So let's say I is equal to 1/2 mr squared. And if we were to plug this in, we would get, what am I doing here? Okay, so the problem now assumes a little differently. So I just wanted to point this out, okay? I wanted to point this out because it is it's a property of, if you have you ever seen that experiment where you have a professor sitting in like a chair, someone spins them, they hold out a weight and they draw the weight in and they spin faster? Yes, that's this, right? So, as an example, we have person holding out stuff. Let's call this omega-1 I1. And then they draw their arms in. And this is omega-2 I2. And by conservation of angular or kinetic energy, really, you can relate these two. But you can also relate them just by angular momentum. So, angular momentum, defined as I omega, we'll derive this. I'm just showing it here. So, L is called angular momentum. And it is always conserved. So L1 has to equal L2. So this becomes omega-1 I1 is omega-2 I2. So I omega-2 is omega-1 over I1 over I2. And remember what we said, I2 is the one where we're drawing ourselves in, right? So I2 gets smaller than I1. And so your final energy increases. Okay. For some numbers to give you an idea, let's assume, well, we'll come back to this. I want to derive this though. So let's go back and derive this. Okay, so what about the work on this problem? Oh, if you want to see the values plugged in, check your book. The book plugs in the values for the yo-yo. Okay. Also, they do it a little differently. They don't assume a final VCM of 0. So they assume it's moving at some speed when it travels this high. So the thing's still moving down, and then you can derive from that a relationship for the average speed.
Which problem is it?
It's an example. So it's like literally after, you know, the chapter in chapter book examples? Yeah, it's one of those. I highly recommend all of you look at those because those, okay, a lot of you probably don't read your books. And I get it. My advice is to read the examples of those books. Read the examples because they do basically what we do in class, minus my own examples I made up, right? Okay, so what about work? So this thing moves, right? Some angle.
Can you move it down a little bit? Thank you.
Right, and then this is F10. So literally F10 is in the direction of your displacement. So this becomes really easy. The work is just F10 dotted with ds, right? And if you recall, ds is equal to r, let's make this r, d theta. And so you have dw equals, actually we don't need this anymore, it's just r hat. This becomes, sorry, not r hat, theta hat. So this is the theta hat direction, this is the r hat direction. Okay. Your displacement is in the direction of theta hat, so that's why it's theta hat. And same here, F10 would be in a theta hat. So this would be F10 theta hat dotted with r d theta theta hat. Putting this together, we get dw equals F10 r d theta. And what is this? Right? We already went over this. This is the torque. So this just becomes torque times d theta. So the rotational work is just your torque times d theta, which is really nice, right? Because we're familiar with that. So the total, so if you want to integrate this, right, it's W equals integral for general. General means it can be applied in any case. If tau is constant, if the torque is constant, this is called tau, by the way. Sometimes I'll just say tau. Yeah. If tau is constant, then we can pull it out, and then this becomes delta. Okay. Very, very nice. Very convenient expression. Another thing. Yep.
Where do we get the ds equals r d theta?
That's just the arc length. That comes from s equals r theta.
Oh,
Right, and then derivative, we have v equals r omega, derivative a equals r alpha. So those are the relationships we'll be using. Keep in mind this is tangent, right? You also have a radial, which is equal to v squared over pi. Okay, another thing, tau, right, is equal to I alpha. So using this, we can have dw equals I alpha d theta, which is equal to I d omega dt d theta. And we can move this dt over because really it's just a change. It's a small change in time. It's proportional to supposedly these two things, so we can do this. dw omega, right? And if we take this integral I omega d omega, assuming in this time frame from initial to final frequencies, if I is constant, then just becomes 1/2 I omega squared minus 1/2 I omega 2 squared. So you're changing rotational kinetic energy. It's just the work on the system. It's basically the same as your the work energy thing. So total work equals total change in kinetic energy. Okay. Power. We never do problems on top with power. I might make another problem. I might make a problem with power. Not this coming exam, but the next exam. Mainly because power. How many of you plan on working for a car company? It's really big here. There's Ford. There's what else? There's a couple of big car companies here. A lot of engineers here get hired by them. And one of the things is horsepower, right? So you gotta know the horsepower and gears. And so a good example in your book is you have one rotating gear, has I, 1 omega 1, and then you have another gear, I 2 omega 2. This is an example in your book. I highly recommend you read it. When you shift gears, these two things have to interlock, right? And so if there's a new speed, right? There's a new speed that has to be calculated. So you have I 1 omega 1 plus I 2 omega 2. And then when you combine them, you get some new I, right? And a new speed. Right? So total angular momentum, L initial, L1, has to be equal to L2. You're fine. Right? And I know I haven't derived L yet, but I just wanted to point this out. Anyways, this relates to rotations, which relate to power. So what is the power? So it's dW dt is equal to d dt of tau z d theta. Remember, when we do this, here we actually have to take the derivative. We can't just divide by dt. If we divide by dt, we're assuming tau z is constant, which it might not be. It could be a function of time. So, but for now, we're going to assume tau z is constant. And then this becomes tau z omega is equal to p. Right? So that's the power. It's just your torque times your frequency. If you recall, power for translation is equal to F dot so tau is really the rotational analog of a force. Remember how I said R cross F? What this does is it takes your orthogonal vector that would contribute to a rotation. So it takes the tangent, it takes this F tan, and then multiplies it by this arm, and then says that's related to a torque. And this torque happens to be the rotational analog of a force. So when you give something a torque, you're giving it a rotational force. Okay? Or In engineering, you would call it a moment. Okay, so what is the rotational analog of momentum? Rotational. Do you know, does everyone know what I mean by analog? Rotational analog, something's an analog of another. Analog is short for analogous, so it means it's just similar to it's a similar in form but different, could be different in interpretation. So rotational analog is R cross P. So R cross P is equal to L. That's the definition. So again, we take the cross product with a momentum, and what are we doing? We are taking the piece of momentum that would contribute to a rotational momentum. Okay? Huh? Definition. So let's look at the particle has some momentum P, and let's call this phi, call this R. So L equals R P sine phi. P, oh yeah, and then let's call this, say it's rotating this way, let's make that positive. So, positive rotation that way. P is mv, becomes R mv sine phi. Here we have mv, R sine phi. That is the piece that is orthogonal to your momentum. So it's the orthogonal piece of your arm. So we'll look at this a little differently. We call this phi. So your book wants to look at it as an orthogonal piece of the arm. In other words, this piece here. But I don't really like that interpretation. I like the interpretation where you're taking an orthogonal piece of your momentum instead. So just keep that in mind. So this is L. Well, I prefer this interpretation, where it's the orthogonal piece of your momentum contributing to this rotation. But they're both analogous, they're the same. It's just where you move the okay, so let's take a time derivative. So L et. Here we have to do the full derivative, so we have dr dt plus p plus r plus. So you treat it just like how you would treat a multiplication. You just do the derivative out like normal. This here is v cross p plus R cross F, right? V and cross P, they're in the same direction, right? So if we look here, P and V, they both point, V is in the same direction, right? So if we look at this becomes M V cross V plus R cross F. V cross V, they're pointing in the same direction, right? So if they're pointing in the same direction, that angle between them is 0. So this becomes 0. And so dl dt to the r plus f, which is just your torque. So your torque is just the change in your angular momentum, just like your force is just the change in your linear momentum, right? Okay. I think that's most of it, so let's just do this. L equals tau dt. Again, if you assume constant force here, or constant rotational force, this just becomes L tau delta t, right? And you can also use I alpha dt, right? And you do that, this becomes I omega. So dl can also be I d omega. And that's where I got this relationship, where L is equal to I. Okay, I think that's it.
Would you go up real quick, please?
Any questions?
Like if you start
Okay, let's do an example. I'm actually going to pull an example from an old quiz.
sort of understand how derivation works, it's just gonna be like wait. Too much for one program. I can see the concepts.
It's going to be a little small. Those are too difficult. My last quizzes were very hard. Okay. Oh, this is. Okay. So this is kind of going to transition into the next chapter, which is statics and equilibrium. We already kind of did equilibrium, but now we can do it with rotations. So let's assume you have a bridge that is like a rod. So I, and then you have a string or a cable that mounts over and lifts.
What is that?
So this is the weight. Let's call it point P. Pivot. And the question is, what is the tension in the system, or the tension here for this to remain static? So in other words, you're pivoting here, so now you need to consider the sum of torques to be 0, right? So if the thing has, the sum of torques is 0, that means the thing is not rotating, okay? So it goes back to the chapter 4 or 5, right? It's going to be the exact same thing. So we have this angle theta, and
Tension cancels out the work. Tension cancels out weight.
so first torque. How many torques do we have in this system? Ignore this. This is not a torque. So we have 2 torques, right? And we need to also define a direction. So we have L over 2, let's call this, let's just call this R. R hat cross the weight, right? And then we have our second torque, which is L, right? L, let's just call this R hat cross this tension, T. So I'm going to define positive rotation to be this way. Okay? So this becomes L over 2 mg, and I point in the direction of my hand and then I curl in the direction of W. So I'm pointing into the board, right? So if I'm pointing into the board, this is negative. And the angle between them is 90 degrees, right? So this is just pi over 2. So that sign becomes 1. And then for this one, it's the other way, right? So I point my hand in the direction of L, I curl in the direction of T, and this one points out of the board, right? So this becomes LT. And this one, though, has an angle, sine theta. Okay, so now the sum of torques into 0, so LT sine theta minus L over 2 mg equals 0. We can just have this be L. So our L's divided out, right? And so our tension needs to be 1/2 mg divided by sine theta. So your tension is actually scaled heavily by this angle. The smaller the angle, the larger the tension, right? And there are limits to this, obviously. So what is the tension equal to? Let's see. If we use a bridge, the mass is about 400,000 kilograms, and the length of the bridge is about 130 meters. And if you take an angle of 30 degrees, this becomes T equals LW over 2. If you plug everything in, this is about 392 times 10 to the 6. All right, and this isn't the full problem yet. We also need to have it such that the sum of F is equal to 0. So we do it this way. We have T sine theta minus W equals 0. That's for your Y's, right? And then you have, for your X's, your pivot point, I forgot to mention this. Your pivot point actually exerts a force, and it has to exert a force. The reason why is because if it didn't exert a force, this bridge would move this way. Right? Think about it. There is nothing stopping the bridge from being pulled this way, because this tension is this way. There's no counterforce. So your pivot point actually needs to have a end there. This is something that you will have to put in yourself when you do these static
It's just
problems.
the length.
You'll have to deduce your direction of n based off the direction of the other forces. Right? So this will become n minus t cosine theta. And so n equals t squared 2. So that's how much force you need to have to keep this thing static. That was one of the questions. What force must the pivot exert to keep static? And this one was, given this, what is T? And it is for static case. Any questions? So what is the tension now if the bridge is rising? Right? So and we're given that theta equals 1/2 alpha t squared. Well, if it's not equal to 0, then the sum of forces or torques is equal to I alpha. Right? So we have minus LW over 2 plus TL sine theta equals I alpha.
It's not static, then it's moving.
And just solve for T.
Isn't there a square root of
T equals 2 C. Oh, I see what it is. Here I solve for alpha,
I think it's
and that's equal to 2 theta over T squared. Because I give you time in this problem. It takes a certain amount of time to raise the drawbridge, right? So you have T L sine theta I.
Let's see what this connection is like.
And I plug in this here for alpha, 2 theta over 2 squared plus. I use a I here to be the same for a rod. 1/3 and square. Right, so if you plug everything in, and I give you a time of 2 minutes, so T equals 2 minutes. So it takes 2 minutes to raise the bridge, and the question is, what's the tension? Right? So by plugging in everything, you get T equals 3.92 times 10 to the 6. Okay? All right. I think that's all for today. Any questions?